Without any further delay, let us begin. And we begin with the title of the course and the word numerical. Just a second. As for the meaning of this particular word, we intuitively know that it has to do something with numbers. It is either relating to numbers or it is involving numbers. Now, if I ask you that what subject deals with numbers, I think all of you would be unanimously giving the answer and the same answer. In fact, even school kids, without a moment's hesitation, would give the same answer as well. And the answer is
Mathematics.
mathematics. That's quite correct. And numerical analysis, as it deals with numbers, is basically a specialized branch of mathematics. It falls in the domain of mathematics. But what does it do? Okay, fine, it falls in the domain of mathematics, but it is something specialized. So what it is supposed to do? It basically deals with algorithms for solving problems of continuous mathematics. Here by deal with, I mean that it creates or makes up, analyzes, and implements certain algorithms. These algorithms are geared towards solving certain classes of mathematical problems. Of course, here I have mentioned continuous mathematics. Here I would just like to mention that maths can be broadly subdivided into two categories: continuous mathematics and discrete mathematics. Continuous mathematics is based on real numbers, or you can say real number line. That is, it is a continuous number line where given any two numbers, one can find another number in between. And in fact, an infinite set of numbers can be found between the original two numbers. It just goes like that if you are given two numbers in a line, you can find another number in between them. And now it becomes a problem of finding another number between one of the extremities and the number that you have found in between the original two. So from there on, it is quite intuitive again that you can find infinite set of numbers between the original two numbers. And that is what is known as continuous mathematics. If you think about a function in continuous mathematics, it is going to be a smooth curve. There are no gaps or discontinuities in between. On the other hand, in case of discrete mathematics, we work with distinct values or discrete values. And given any 2 points, there aren't any infinite number of points between them. You can think of a finite set of objects. So basically, the natural numbers are the domain of continuous mathematics. And let's say, for example, if you consider the Fibonacci series. So it is 1, 1, 2, 3, 5, like that. So these are discrete numbers. You cannot have another Fibonacci number in between 3 and 5. That would be violating the definition itself. So that is the distinction between continuous mathematics and discrete mathematics. And numerical analysis is basically solving problems of continuous mathematics. Now let us come back to numerical analysis itself. And we can say that the objective of numerical analysis is to reformulate mathematical problems in such a way so that approximate solutions can be obtained with arithmetic operations only. So here, two important things are to be noted. One is that we prefer arithmetic operations instead of symbolic manipulations. What do we mean by symbolic manipulations? We do symbolic manipulations in algebra, or we do it in calculus. So you have x square, you want to differentiate it with respect to x, you obtain twice of x as the output, the result. Same for integrations as well. But instead of that, here in numerical analysis, we prefer arithmetic calculations, arithmetic operations. The basic arithmetic operations are, of course, addition, subtraction, multiplication, and division. And these are performed on numbers. With just that much, we are looking to find out problems to certain complicated classes or solutions to certain complicated classes of mathematical problems. Let me just give you one example. But before that, let's say that mathematical problems are formulated so that they can, and often these arithmetic operations are repeated. So repetitive arithmetic operations are performed in order to solve these mathematical problems. Now, obviously, mathematical problems have their own definitions. So basically here, instead of formulated, it would be better if we write reformulated. Let's come to the example. Let's say I is defined as a definite integral like this. Integration a to b, that's the lower limit, the upper limit, fx dx. We are familiar with this. Here, fx is a general function. It could take any form. Physically, what does it mean? We know that it means if we plot x along this axis and fx as the y-axis, then its general function would be something like this. Here is the point A on the x-axis, and here is point B on the x-axis. So what does this integral mean? What is its significance? How do you interpret it?
Area under curve.
Area under the curve. So when I evaluate this integral, what I would be getting is this area under the curve. Now, depending on what this function is, it could be x square plus something, could be 3x square plus 5x cube plus 2x to the power 4, any function of x it could be. And depending on that, the form of this curve would change, but the definition remains the same, that you would obtain as answer to this integral what is the area under that curve. Analytically, we know how to solve that. So that is the formulation of this integral. But suppose I represent this area as a trapezoid like this. This trapezoid. So if I calculate that area, this area can be calculated very simply using arithmetic operations. What is to be done? How do you get the area?
So, parallel lines that are...
Yes, the summation of the two parallel lines multiplied by the
distance between them.
Distance, perpendicular distance, the shortest distance between those two parallel lines. So it's a basic mathematical, or I should say arithmetic operation.
Into half of an, sir?
Yeah. That is there. Means what I want to say here is that you would be performing very basic arithmetic operations, and that would approximate to some extent the area under the curve. Now, if you want to better that approximation, I can do this. I can break up this interval into two and make two trapezoids. Now you can calculate in the same way the area of these two trapeziums and add them up. So that would be a better approximation. I can go on subdividing these intervals like this. I can make hundreds of divisions over here. And if I add up those areas of 100 trapeziums, I would get a pretty good approximation of what is the value of this integral. Do you agree or not?
Yes, sir.
Yes, sir.
That is quite possible. And that is what is basically done in numerical analysis. We reformulate a known problem, known mathematical problem, in such a way that only on the basis of certain basic arithmetic operations, we can get the results. So again, I reiterate 2 points regarding the objective of the numerical analysis. One is that we prefer arithmetic operations, often repetitive arithmetic operations, to symbolic manipulations or the exact methods. And the second one is, and it's quite important to remember, that the results provided by the numerical analysis is an approximate result. Think about the trapeziums. They are not going to give you the exact area under the curve. You can approach the exact area by increasing the number of intervals and thus the number of trapeziums, but there would be certain errors associated with it. So numerical analysis is inherently giving us approximate results, and that is in another way saying these results have errors in them. Some amount of error is going to be inherently linked with the numerical result. Now, of course, if this error is too high, then you do not have a successful numerical procedure, numerical analysis. You have to bring down the error to some acceptable limit. That is also a part of the numerical analysis study. How do you minimize the error and keep it under a certain level so that it gives us acceptable solutions? Now let us move forward. We have just talked about one example here. And you can think of so many different types of or classes of mathematical problems. Here I have talked about an integration. You can have a differentiation, or you can have certain equations, mathematical equations. Mathematical equations can be of different types. You can have a nonlinear equation. You can have linear simultaneous equations or differential equations. In differential equations, again, you can have ordinary differential equations or partial differential equations. So all these different classes of problems are present. And it is, of course, very easy to understand that there would be many different types of numerical techniques or numerical analysis to cater to these different types of problems. But one thing remains the same. And what is that? The common characteristics of these numerical methods, different numerical methods, are that all of them deal with large numbers of tedious arithmetic calculations. There would be very large number of arithmetic calculations that need to be performed to give you acceptable results with minimum error. You can say that is one of the drawbacks of the numerical analysis. Now, of course, this would be a drawback if you are trying to solve these problems by hand. But fortunately, we have something in our daily life, in fact, in our society, that is very good in handling large number of tedious arithmetic calculations. And what is that?
Calculators.
Computers.
Computers. Calculators or computers. In fact, scientific calculators also are kind of computers, you can say. But anyway, the answer is computers. Modern digital computers. They are efficient and fast in dealing with large numbers as well as very small numbers. And they are proficient in repetitive operations. Probably they can perform thousands of iterations in a matter of seconds, a fraction of seconds. So that makes the modern digital computers an extremely useful tool in case of numerical methods. With the help of these computers, high computation capability computers, different types of numerical methods can be successfully applied to different fields. Again, go back to the integration problem. As I said, if you make two divisions here, that is quite easily done by hand. If you know what is A and B, what is the middle value, probably you can take A plus B by 2. And the functional values at A and B, you will probably able to calculate that in a matter of minutes. If it goes up to 10, then also it is doable by hand, but it requires certain concentration and a particular level of effort. However, if you make 1,000 divisions between A and B, then it becomes really difficult, if not impossible, to solve by hand. But if you can develop an algorithm which you on the basis of which you can generate a program, and that program is fed to a computer, the computer would be able to do that calculation without any problem within probably 5 or 6 seconds. So that is where the advantage of modern digital computers are in terms of the numerical analysis. Of course, in this particular course, we are going to learn about different numerical methods, and we'll also learn about how to implement those numerical methods by creating algorithms and then subsequently creating C programs that can be run on computers. Now let us look towards the syllabus of this numerical analysis course. This is just the syllabus that is given there, and you can read through it, and you can see that there are certain modules here. For one thing, I can say that equation solution is one module, interpolation is another module, curve fitting can be taken as another, you can say, sub-module, and finally there are also differentiation and integrations. If we talk about in terms of course outcomes, that is what you will learn from this course once you have completed. So what you should be able to do at the completion of this course. 4 things we are looking at as course outcomes. The first one is that you should be able to solve algebraic equations numerically. Second is solve differentiation, integration, and differential equations numerically. The third one is that solve interpolation and regression problems numerically with applications. And associated with all these three course outcomes is the fourth one, which is to develop computer programs for these numerical methods. If we collect all these course outcomes together, these are the course outcomes that we are looking at in this numerical analysis course. So at the end of it, you should be conversant with solution of algebraic equations, differential equations, solving interpolation and regression problems. Not only that, you should be conversant in developing computer programs for these different numerical methods. So what approach we will follow in this course is that, first of all, the basics of the theory about the numerical method would be discussed through presentation or some given material. And once that is done, the next step would be to develop the algorithms based on those theories that were discussed. And the final step would be to develop C programs based on the algorithms that were developed. So that is the thing that we will follow. Now here, I have mentioned the definition of the numerical analysis again, and you can say that I have made just one small modification to the previous definition. Now we can define numerical analysis as the domain of mathematics that deals with, that is, it creates, analyzes, and implements algorithms for obtaining approximate solutions to problems of continuous mathematics. Why the word approximate comes in, we have already discussed in the first slide. That is, errors are inherent in these numerical solutions, and that is why these are known as approximate solutions. They are not exact solutions. But here, one more thing that needs certain discussion is that where do these problems come from? What is the origin of these problems of continuous mathematics? Are they given in the exercise of a numerical analysis book? Those are the things. Or is it given in some assignment sheet or problem sheets? Definitely not. Where these problems originate are basically real world applications of algebra, geometry, and calculus. And where they can be found is throughout the natural sciences, social sciences, medicine, business, as well as the engineering domain. In our case, in the present case, obviously we are more interested in the problems of the engineering domain. Sorry. But if we talk about problems in general, we can have two different classes of problems. One is analysis. That means you have a system, existing system, you want to analyze it based on its different properties, parameters, dimensions, and so on. But it is an existing system, and you study its behavior. On the other hand, you can have a synthesis problem or a design problem. That means you design something, you create something new to cater to a particular problem. Solution to a problem is design. So you can have either design or analysis of a system. But in both cases, what helps us immensely is if we can develop an abstract model of the system. So basically, we are going from the qualitative domain to a quantitative domain. So we have abstract model of the system that simulate the system behavior. And what can act as these abstract models are, of course, mathematical models. Mathematics would be immensely helpful here. Let us now define what is a mathematical model. A mathematical model is basically a formulation or an equation or an expression that represents the essential features of a system or process in mathematical terms. We can write a general mathematical model or mathematical expression as shown here. You have on the left hand side a dependent variable, and it is equal to the right hand side, which is a function of independent variables, parameters, and forcing functions.
Sir,
Yes, go ahead.
sir, what is forcing functions?
I'll come to it. I'll definitely come to it. One by one, let us discuss. What is dependent variable, first of all? It is a characteristic that usually reflects the behavior or state of the system. Think about a particle moving in 2 dimensions. How can you define its state? Its velocity is
velocity
changing
and-
with respect to time. So velocity can be considered as a state. Absolutely correct. Velocity.
The direction.
Or
Velocity money direction.
velocity
money direction.
is it considers direction itself.
Sir,
Or you
position.
can consider its position.
Position.
At time t, it is at position x1, y1. At time t dashed, it has moved on to another position, say x2, y2. So if you know these 2 coordinates, you know the system behavior or the state of the system, where exactly is that particle. So that is the dependent variable. Now, what is the independent variable? It is probably you can say dimensions such as time or space. You think about velocity changing with respect to time. So time is the independent variable here. In a 2-dimensional space, a particle is moving, so at certain time it will obtain or attain certain position. So here the time remains the independent variable, and the coordinates of that particle would be the dependent variable. You can also think about a beam. You have studied deflection of beam in previous semesters, I hope, probably in strength of materials. So if you have a simply supported beam and you put a concentrated load in the middle, what happens? The beam deflects. The maximum deflection would be at the middle. Obviously, at the end, there would be zero deflection because it is zero transverse deflection because it is supported at the 2 ends. Now, if you attach an axis along the length of the beam, so if you move along the length of the beam, you will see that the transverse deflection changes along that axis. So here the coordinate x is the independent variable, and the deflection along that transverse direction, that would be the dependent variable. What are parameters? These are basically system properties or composition. The beam has a particular material, and that material has some Young's modulus. If it is a steel beam, it would have elastic modulus of say 200 G. If it is an aluminium beam, it is going to be around 70 G. The deflection would be the same under same loading? Definitely not. So composition of the beam plays a part, and that can be taken as a parameter. Similarly, the cross section of the beam could be different. I section, L section, C section, or a simple circular section, or even a rectangular section. So all of these different sections would be having some different moment of inertia that could be considered as another parameter. So these are known as system properties or composition. They affect the system behavior. Now we finally come to forcing function. These define the external influence on the system. Again, think of the beam. I'm applying a concentrated force at the midspan of the beam. So this is the external influence on that system. And that can be construed as the forcing function. Forcing functions can be independent of time, or it could be dependent on time as well. If it is a static situation, as in case of the simply supported beam subjected to a concentrated load, then time does not play a part. So it's a time independent forcing function, external influence. But in other situations, the force may be varying with respect to time as well.
Sir, in case of distributed load, it is depends upon the coordinate axis.
Yes, it could be dependent on the coordinate axis as well. It could be a triangular shape or hat shaped loading. Then also it is dependent on the longitudinal axis that you have attached with the beam. It is also possible. So there are various possibilities here, but overall, generally speaking, external influences acting on the system can be taken as forcing function. You can think of other type of systems as well. For example, think of a pendulum. I think in physics in +2 level or even mechanics, you would have studied pendulums, simple pendulums. So you have a hinge point here. That is the vertically downward equilibrium position. Sorry. And let's say this is the pendulum. So from its equilibrium position, you have taken it to one side and let it go. So what will happen? It will execute a motion like this. So here, theta could be considered as the dependent variable. So displacement, angular displacement with respect to time. Dependent variable is of course time. As time passes, theta changes. So time is the independent variable, theta is the dependent variable. What about the parameters? We have the pendulum length of L, which is one parameter. The mass of the pendulum M would be another parameter. And what is the external influence here?
Air drag or gravity.
Gravity. So you have this gravity field. So that would be the forcing function or external influence. Also, if it is moving in air, of course, air would be providing some resistance to it. You can better visualize it if you think about the pendulum moving in some viscous medium. So that would also provide some air resistance, and that would be again some external influence on the system that would dissipate the energy of the system. So I hope this part is clear, how we can consider a general mathematical model. Now, obviously, that is a general expression. The actual mathematical expression, it could be something very simple, an algebraic relationship, or it could be something very complicated, complex, with large number of differential equations in a single set. Depends on the complexity of the system. If it is a simple system, maybe a single equation, single linear equation would be enough. But if it is a complicated system, a continuous system such as a beam vibrating under some external influence. Then, of course, you have to have other complicated differential equations to describe its motion. What are the different mathematical operations or procedures that are part of the mathematical model? They could be differentiation, or could be integrations. This mathematical model could be nonlinear equations or simultaneous linear equations, could be differential equations as well. Now, at this point, let us again stop for considering another example. Let's take up Newton's second. What is Newton's second law? Anybody?
F is equal to ma.
The change of momentum in any direction is equal to the mass and is equal to the mass into acceleration of the system in that direction.
Okay, I heard two answers. One was the statement of the Newton's second law, and the other one was the mathematical expression of that second law. If you ask this question to maybe 100 people, you will definitely get these two answers. Somebody will simply say, second law, oh, that is F is equal to ma. That is a mathematical model of the physical law that is described, that you described quite well. So we have the second law. Let me just write it out here. That is F is equal to ma. This is the mathematical representation of the Newton's second law. You have the force, the mass, the acceleration. Now, this can also be represented as, let's say, I write it as A is equal to F by m. Same thing. So, acceleration could be considered as the dependent variable. F is, of course, the forcing function, and m is the system parameter. Now, what is missing here? Is anything missing from this mathematical model?
So directions.
The independent variable is not there because it is missing because we are not at this point trying to predict something. The independent variable comes in when you try to predict. What would be the deflection at x equal to say some distance from the left hand support? What would be the position of the pendulum at time t equal to say 5 seconds? So you are trying to predict something, and that is when the independent variable comes into picture. At this very simplified mathematical representation of the second law, that predictive nature is not yet present here. But of course, this acceleration can be represented like this. Rate of change of velocity with respect to time equals to F by m. Now, if we think about a body falling vertically downward under gravity, let's say we are thinking about a box of supplies or relief material being airdropped in a flood affected region with the help of a parachute like this. So it's an engineering problem. So as it comes down, the velocity now can be predicted with the help of this equation. But of course, we need to take into account all the forces in this system. And what would be the forces? Obviously, it is falling under gravity. So F can be represented as, say, the weight, let's say Fg, acting vertically downward. We'll consider downward as positive. And there would be something else as well, the air resistance. Let's say that is represented by Fr. Now, Fg can be quite easily written as this, m being the total mass of the system. And this part, this air resistance, for now we assume that this is proportional to the velocity. So we can write it as minus c into v, where c is the proportionality constant. It is known as the drag coefficient. So we can simplify this. dv dt is equal to g minus c by m How do we solve for the velocity? We have to solve this differential equation, and there are rules governing the differential equations. You know all of that from your +2 level calculus, and if I give you this problem, you will be able to solve it quite easily. And finally, what we will obtain is an answer for this. This will be expressed again in terms of a say mathematical expression, which will consist of these system parameters as well as the independent variable. But that is solving it in terms of the exact procedure. What if we can solve this numerically as well? And that is quite possible. For that, let us just consider that dv dt is basically limit t tends to 0 del v del t. That is the formal definition of this differentiation. If we ignore this part, we can write it as del v del t, with t being increasingly smaller. We cannot physically make it approach 0, but we can take it smaller values of this interval. We can also write this as phi I plus 1. I is basically the velocity at time instant ei plus 1. And this is t. It can be approximately written as this. So now if we know the starting velocity, that means at time instant t equal to 0, what was the velocity of this object? We can calculate what is this. Given all of the other parameters are provided to us, all these are known, then we can calculate what is vi plus 1. So here we have not solved it directly. by the exact method. What we are doing is basically we are taking help of some very basic arithmetic operations in order to get an approximate result. And that is what is done in numerical analysis. Is this part clear?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay. So let's move forward and just give you a few other examples, such as this projectile motion. So how it can be mathematically represented? You know these equations from your mechanics classes. So x is given as s0 cos theta multiplied by t. What is s0? The initial velocity. And theta is the angle at which the particle is, say, let's say, thrown. Similarly, the vertical distance y is given by minus half gt square plus s0 sine theta into t. Both of these can be combined also in this equation. Nothing complicated. We have just replaced t and made it implicit. Now this equation is a nonlinear equation. If you think about the first equation here, that is x equal to s0 cos theta into t, then x is the dependent variable, of course, position at time t. S0 and cos theta would be the system parameters, the velocity at which it is thrown, and the angle at which it is thrown. T remains the independent variable. Similarly, you can analyze the second equation, y, also, and find out what are the dependent variable, independent variable, and system parameters. Of course, in both the cases, gravity acts as the external influence. But when we put these two together, then time becomes implicit. Time has been removed from this equation. Now you can consider maybe y as the independent variable. And if you supply the value of y, then at your hand is a nonlinear equation, a quadratic equation. You can think of the other way as well. You can supply x, then x becomes the independent variable. For a given x, you find out the value of y. That is a relatively simpler problem. But if you go for the reverse one, that means the height is given, you are trying to find out a particular x corresponding to that y. So basically that equation is nothing but a quadratic equation of this form. We know how to solve it. If I tell you, you will just from your memory tell me what is x. And it is ingrained in us from our school days. So that is not a problem. But the problem arises if this changes to some higher value. If this was a cubic equation, then obviously that analytical solution is there, but we do not remember it, or we do not have it imprinted in our memory. So obviously then you have to solve it by hand, which could be difficult. The solving of nonlinear equations is also a very important part in numerical analysis. And we will be, of course, learning about numerical methods to solve for nonlinear equations. The next example is more complicated. It's to do with Euler-Bernoulli equation, which describes the transverse deflection of a beam under loading. This is the equation. So you see that it is a differential equation, and it relates the beam deflection W with the external loading Q. Q could be anything. It could be a concentrated load, or it could be a distributed load, uniformly distributed load, or even a triangular load. It could be anything. Also, note that here we have the parameter I, which is the moment of inertia. And it is expressed as a double integration over z square dz dy. Similarly, the dynamics of Euler-Bernoulli beam can be expressed in terms of partial differential equation. The previous one was an ordinary differential equation. This is a partial differential equation. And just for your interest, create interest in you, this is a simulation of the free vibration of a cantilever I-beam. And this simulation is generated by the solution obtained from the second equation shown here, this equation. So the point I'm trying to make is that mathematical models could be varied in nature. It could have different mathematical operations or mathematical procedures ingrained in them. And different types of numerical methods, numerical analysis procedures are there to cater to different types of mathematical models. So we have at the beginning a qualitative problem definition. From there, we have moved on to a quantitative mathematical model. Think about the airdrop of supplies in flood-affected regions. That is the qualitative description of the problem. The mathematical model that describes quantitatively, we have seen that expression, mathematical expression. Obviously, it's simplified, but it is a mathematical model nonetheless. Now, these mathematical models are obviously based on scientific theories. The case under consideration now, it was derived from Newton's second law. So, it is based on scientific theory. Any mathematical model would be based on scientific theory. Any valid mathematical model, I should say, would be dependent on a framework of valid scientific theories. Not only that, sometimes mathematical models need to be augmented with the help of experimental data. So experiments may be performed in order to have an appropriate mathematical model. However, in this course, we are not interested in converting a problem, qualitative problem, to a quantitative mathematical model. We'll assume that the mathematical model, the mathematical expression is available with us. What we are interested in is basically how to obtain the results. Results can again be numeric, that means a set of numbers or a single number, or it could be graphic, that means the result is obtained in terms of a plot. So our interest is in the solution of these equations or evaluation of these expressions. It's basically the problem solving tools. And that is where the numerical analysis comes in. But before that, let me just also mention that obtaining the results is not the end of the problem. You have to think about implementation as well. So if we have societal interfaces, then depending on the problem, you could have scheduling issues, optimization problems, communication, or public interaction. You cannot just solve a mathematical model and be done with it. You can get the velocity required for dropping the supplies in the flood affected zone, but if you do not implement it, it doesn't do any good. So obviously, you have to keep in mind that the results that you obtain should be applied, should be implemented. Anyway, that is besides the point. What we were talking about is basically the solution or evaluation of mathematical equations or expressions. And there exist two broad classes of methods to obtain solutions to an equation or evaluate an expression. We have already probably indirectly alluded to that there are exact methods and there are approximate methods. These approximate methods are the ones that we are interested in this course, and these are the numerical methods. What are the exact methods? They provide analytical solutions, but they provide it for only a handful of very simple category of problems. For complicated type of problems, solutions are often not available at all. If you think of any sort of derivations that you have performed in your strength of material classes, the first thing that you do for derivations is take certain assumptions, is it not? So those are the simplifying assumptions. On the basis of that, the problem is simplified, and then only the exact methods can be applied to solve them. So obviously, it does not work for more complicated type of problems. And definitely, if it has to be applied, one needs to have very good grip of mathematical computations, mathematical procedures. And it is sometimes, even if you have that level of competency, it is inconvenient to do that because these procedures are quite long and convoluted. So exact methods are not exactly simple ones. So what is the alternative? The alternative are, of course, the numerical methods, which are extremely powerful for problem solving, and they are capable of handling large system of equations or even non-linearities or complicated geometries. And such occurrences, means such instances of nonlinear equations or complicated geometries are very common in engineering practice and problems. Think of a system of equations which has 100 variables and 100 equations. Now we know from our school days how we can solve simultaneous equations of two variables. If I give you such a problem, you will very quickly solve that by hand. Now if the number increases to three equations, three variables, just a little bit more complicated. I would not say even complicated, but it will be a lengthier procedure. But in the end, you will obtain the solution at the end of one page of calculations. But what if there are 10 equations and 10 variables? Extremely difficult, laborious process. And if it becomes 100, then you cannot even think about solving it by hand. Only option available there is the numerical method, which would provide you with probably not the exact solution, but it would provide you with an approximate solution with some errors, but those errors would be under certain acceptable limits. And that is the advantage of numerical methods. Now, our course is, of course, dependent on writing programs in computers for numerical methods. So it is prudent to think about this computer implementation of numerical analysis here at this point. But it should be remembered that numerical analysis existed before the invention of modern computers. In fact, even in say prehistoric times, thousands of years back, there are instances of some numerical methods, primitive numerical methods that were applied and good results were obtained. One such example I can show you here is this Babylonian clay tablet named YBC 7289. When it was made, probably 1800 or 60 to 1600 BC, which this tablet, this procedure which is there on this clay tablet, it is a numerical method to approximate the value of root 2, square root of 2. This approximation is accurate up to 6 decimal places, and you can read about this particular procedure. I'm not going to discuss it. It's going to take up quite a lot of time. That I've given the link. You can go to this link, or you can put an YouTube search. You can find out about this tablet, and it's a very interesting topic. I suggest that you follow through on this. So, numerical methods existed before computers. But at that time, obviously, such computations were carried out manually. And again, quite obviously, it required a lot of repetitive work and took up a lot of time. But in certain situations, such as, say, calculations to do with military applications, there were thousands of people who were employed to do such manual calculations. But everything changed after probably from the middle of the last century, 1950s, after the Second World War, when there was exponential growth in power and availability of digital computers. What has happened due to that is there has been an increasing use of these numerical methods in analyzing realistic mathematical problems. More complicated geometries, more complicated systems are being looked at through these numerical methods, be it in the field of science, medicine, engineering, or business, doesn't matter. Complicated systems are now being analyzed through different numerical methods, simulation techniques. And it's quite easy to understand that due to the capabilities of the modern computer, it is far more easier to set up the problem, solve the problem, and interpret the available results through numerical approach. You have dedicated softwares to cater to different simulation needs of different kinds of mathematical problems. Let us come back to this graphical representation of how we go from the problem definition to its implementation. As already mentioned, we are basically interested in the solution part. That means how we obtain the solution, go from the mathematical model to the results. And that is where the computer can help us. How can we implement this in a computer? First of all, of course, you need to develop the logic of the problem solution. That means you require an algorithm or a flowchart. You have to develop it. Based on that algorithm or flowchart, you create a source program in high-level language. You compile that with specialized compilers. You get a sequence of machine instructions. So basically, a sequence of zeros and ones that is understandable by that machine itself. These are known as object programs, and these are low-level languages, basically machine languages. And once you have the object program, that can be executed to get the output or the result. So this is where the numerical method and the help of the computers come. In our case, obviously, the logic of the problem solution would need to be developed first. Then we'll move on to the C environment, dev C++, and there we will write the code, the source program, source code for that particular numerical method. Once you run that code, hopefully you will get correct results. Now, one more thing that needs to be understood at this point is that various softwares are presently available to handle complex problems through in a very efficient and simple manner. What you need to do in case of these softwares is basically supply the inputs, and they will give you the results or the output. How that happens is because these softwares already have functions that use standard numerical methods. Just to give you an example, matrix inversion is a very important operation in various different fields. And if you want to write the code for matrix inversion, it will probably take up 200 or 250 lines in C. However, such functions that perform matrix inversion is already available to us in certain numerical environments, such as maybe MATLAB. MATLAB has already got a pre-existing routine that computes matrix inversions, inverse of a matrix. And what you need to do is just supply the matrix and write one line of code that would give you the result. So users can pass the required parameters and get the expected results, appropriate results, just by a single command. In MATLAB, that is INV. INV within bracket to provide the matrix. And that would give you the inverse. So why waste time in writing 250 lines of code? Basically, there is no need for deeper knowledge of numerical methods. You just supply the input, treat it as a black box. Out of the black box comes the result. So you need to ask the question, why should we learn about numerical methods? There are three reasons that I'm going to give you. For the basic understanding of theoretical background of numerical methods, first of all, available methods may not be that efficient. You may be working on a specific problem where such methods may not be available at all. These usually happen in case of research problems. Quite often, in case of research problems, you venture into an area where you do not have something that is required for your specific need. So obviously there, you need to devise your own programs. based on appropriate numerical analysis. Second, how do you choose an appropriate method if there are multiple options available? So obviously you need certain background knowledge about it. Background knowledge such as how fast a numerical method converges to a solution, or how much error the final solution is going to have. Different types of numerical methods are going to have different convergence rate, different amount of error also. So in case of a specific situation, if you want accurate results in best possible time, optimum time, then you have to be able to choose the appropriate numerical method. And the background knowledge of different aspects of various different numerical analysis procedure is going to help you in that. And finally, in case there is some unexpected results, you have got a problem, you have run a numerical methods procedure, numerical analysis procedure, but what you get as output, your result, is not what was expected. It varies from the expected results. So obviously, then you need sound background to comprehend what has gone wrong, to interpret those results and modify probably the numerical method itself or give other type of inputs so that you get the expected results. So these are the three main reasons why you should invest time on numerical methods and have some in-depth theoretical knowledge about it. And that is what this present course is geared to. So that brings us to the end of the discussions. Only one more slide is left, and that summarizes what we have discussed over the last 1 hour. First of all, numerical methods are mathematical tools to obtain approximate solutions for real-life complex problems that cannot be obtained easily. And these mathematical models of such problems require solution of nonlinear equations, solution of simultaneous linear equations, maybe interpolations, regression, differentiation, integration, or it could be solution of differential equations. All these things are there in the present syllabus, and we'll be looking to address all these topics. As already mentioned, numerical methods are approximate methods because errors are inherent in these numerical solutions. There are various sources that may introduce errors, and that would be the topic of discussion in our next class. Numerical methods deal with large number of arithmetic computations, and that is what makes it amenable to computer programming. So that brings us to the end of the class today. Thank you for your attention. Do you have any questions?
Sir, is there any basic book we have to follow, sir?
Yes, sir.
There is no specific book at this point of time. Let me just go to the next class, and in the next class I will give you a list of maybe reference books that you can refer to. Okay.
Okay, sir.
Okay, sir. And sir,
স্যার
yes.
অ্যাটেন্ডেন্স নিয়েছেন স্যার
Yes, go ahead.
স্যার বলছি যে অ্যাটেন্ডেন্স নিয়েছেন
তোমার রোল নাম্বার কত?
স্যার 30 আমি একটু লেটে জয়েন করেছি
30. Okay. Anybody else is there? Shobhan Maiti, Joydeep, Shahjad Sheikh, Wasim Bari. Any one of these four? No. Okay, fine. Any other questions? Do you have any questions?
Sir, do we have to make any specific changes for the Deep C++ and if we want to proceed numerical analysis in Deep C++, sir?
No, I don't think so.
এমনি যে যা
Changes
কনফিগারেশন আছে সেটাই হয়ে যাবে।
তাতেই চলবে যদি
সেম
আমরা
আমি একটা করেছিলাম তো সিমসনটা।
গ্রাফিক্যাল রেজাল্টস যদি পেতে চাই, মানে গ্রাফিক্স যদি ইনকর্পোরেট করতে চাই, তাহলে হয়তো
MATLAB
কিছু চেঞ্জ করা যেতে পারে ডেভ সি প্লাস প্লাস এনভায়রনমেন্টে, বাট আই ডোন্ট থিঙ্ক ইটস অ্যাডভাইসেবল অ্যাট দিস পয়েন্ট।
ওকে
স্যার MATLAB ইউজ করতে পারি তো গ্রাফিক্যালের জন্য, মানে ভালো বলতে কি?
প্লট করার জন্য অবশ্যই,
হ্যাঁ
নিশ্চয়ই করতে
অনেক অনেক সুবিধা স্যার।
ইটস মোর ইউজার ফ্রেন্ডলি। এক্সেল ইউজ করতে পারো, বাট MATLAB is MATLAB will provide you with lot of options regarding plotting and graphics.
সিমুলেশন সফটওয়্যার কি কিছু শিখতে হবে আলাদা করে, মানে MATLAB ছাড়া?
Simulation software,
মানে
again, MATLAB is not a simulation software, by the way.
MATLAB
is a
computation
ID.
software.
ID, it's a specialized ID, integrated development environment, but simulation software at this point is not necessary.
মানে স্যার কিছু শিখলে
স্যার মোটামুটি স্যার
তোমার
আমরা এখন
নিজের ইন্টারেস্টে অবশ্যই শিখতে হবে।
না মানে স্যার কোনটা ভালো এটা একটু জানতে চাই।
স্যার বলছি আমরা এখন ধরুন মেকানিক্যাল সেকেন্ড ইয়ারে আছি, তো আমাদের এই পয়েন্টে মানে আমাদের কি কি বেসিক স্কিলস নিলে আর কি মানে আমাদের মানে পরবর্তীকালে সুবিধা হবে?
এখন অলরেডি তোমাদের আমি বোধহয় লাস্ট ক্লাসে রেফার করেছিলাম যে তিনটে টাইপের সফটওয়্যার হয় মেকানিক্যাল রিলেটেড। এক হচ্ছে তোমার ড্রাফটিং সফটওয়্যার, দ্বিতীয় হচ্ছে তোমার সিমুলেশন দি সলিড মডেলিং সফটওয়্যার, 3D modeling software, and finally there are simulation software, analysis software. Analysis software এ overwhelmingly যেটা ইউজ হয় সেটা হচ্ছে ANSYS. It's a finite element software. তোমরা অবশ্যই শিখতে পারো। There are lots of
তারাই তো স্যার ওই মানে ওভারলোড হচ্ছে না, তারপরে নরমাল লোড কন্ডিশন এগুলো করা হয়।
not only that মানে এটা তো জাস্ট একটা স্পেসিফিক এক্সাম্পল। ANSYS can do a lot of things. ANSYS is basically a finite element software. Finite element is a variational procedure. There would be probably electives on finite elements later on towards third year.
আচ্ছা স্যার
তো সেটা তোমরা নিতে পারো। That will obviously augment your learning about ANSYS. But it's not that যে তুমি finite elements জানো না মানে তুমি ANSYS শিখতে পারো। It is possible to pick up the basics of ANSYS through some online tutorials. There are lots of tutorials available, but finite element basic idea থাকলে সুবিধা। So I would say that keep that for later on. Right now তোমাদের কোর্সে AutoCAD রয়েছে, drafting software রয়েছে. So first of all learn drafting software quite well. Next year you will have solid modeling. So learn solid modeling through SolidWorks. এই দুটো প্রথমত তোমাদের প্রাইম ফোকাস হওয়া দরকার। Finally ANSYS is of course there. ANSYS শিখতেই পারো। There are other finite element software, simulation software.
অ্যানসিসটা কি স্যার আমাদের এর মধ্যে আছে, সিলেবাসের মধ্যে আছে অ্যানসিসটা?
না, ANSYS
না
ANSYS is not included in the
আর আমাদের ওই মানে ক্যাডেও তো 2D টা শুধু আছে না, 3D টা তো নেই।
কম্পিউটার এডেড ড্রাফটিং এ এখন যে তোমাদের এই সেমিস্টারটাতে যেটা চলছে কম্পিউটার এডেড ড্রাফটিং, সেখানে 3D নেই। 3D তোমাদের 3D মডেলিং তোমাদের শেখানো হবে থার্ড ইয়ার সেকেন্ড সেম। SolidWorks is there in the curriculum.
আপনি নেবেন তো স্যার?
সেটা কি করে বলবো এখন থেকে। তো তোমাদের দেখো 6টা সেকশন, কোনো না কোনো একটা সেকশন তো থাকে, আমার ইউজুয়ালি থাকে। এত আগে থেকে তো বলা সম্ভব নয়, রুট চেঞ্জ হয় প্রতিবার। ইউজুয়ালি আমি একটা সেকশনে নিই। which section it's going to be, that's too far in the future. So আমার সাজেশন এট দিস মোমেন্ট AutoCAD ভালো করে শেখো। AutoCAD ইন্ডাস্ট্রিতে মেজরিটি জায়গায় অটোক্যাড চলে, অটোক্যাডের রেসপেক্টেই ড্রয়িং হয়, দ্যাট উড অ্যাড টু ইউর স্কিলস সিভি। সলিড মডেলিং শিখতে পারলে অবশ্যই দ্যাট উড বি অ্যান অ্যাডভান্টেজ। আর অ্যানালিসিস সফটওয়্যারটা মেনলি রিসার্চ পয়েন্ট অফ ভিউ থেকে ইম্পর্টেন্ট হয়ে যায়, বাট কিছু কিছু ক্ষেত্রে তো ডেফিনেটলি অ্যানালিসিস সফটওয়্যারও ইউজ হয়। ফর দ্যাট ম্যাটার অটোমোবাইল ইন্ডাস্ট্রিতে ক্রিও প্যারামেট্রিক ইউজ হয়, আই নো। বাজাজ, হিরো হন্ডা, হিরো মোটোকর্স, they use ANSYS, if I am not wrong. So different industries use different types of software, but the thing is that if you can pick up these skills in one particular software, it's not too difficult to transfer it to another software, because the basics remain the same. Okay, Wasim Bari wants to join. 12:30.
আরে ও ভেবে যে 3 ঘন্টা ক্লাস হয় তো।
I think we can let him join. Yes, Wasim, you're too late for this class. Are you there? Wasim? I think he can't hear me. Okay, if there are no questions, I'll stop today's class here.
Okay, sir.
And errors, origin of error, sources of errors, quantification of error, and how error can be minimized. That we'll be looking at in the next class.
এটা কোনো বই কিনতে হবে?
স্যার বললো
Books I'll let you know in the next class. Okay, আজকে তো just introduction হলো. Let's start these topics proper, then we can discuss about books. Okay, so no more questions. I can stop the presentation. Thank you, and of course I will send the recording. তোমরা আগের
PPTs গুলো একটু শেয়ার করে দেবেন স্যার।
PPT I will share. PPT I will share as
ক্লাসরুমে দিয়ে দেবেন।
হ্যাঁ, ক্লাসরুমে দিব। যে তিনটে জিনিস I will share. First of all, the PowerPoint show. The second is a PDF of the slides, and the third thing is the recording of the class. Okay.
Yes, sir.
So
Thank you, sir.
okay.
Thank you, sir.
Okay.
Thank you, sir.
See you next week.